Yeah, then start. Let me start presenting you the slides from the top. Are you able to all see this? See the slide? Right. So as in the previous week, I had discussed the overall process. How do you use it in a finite element methodology? The steps. So if people are new, basically you need to first have the CAD model to make sure that you are assembling it as close to the actual field model is. Then you are to run through the process of defeaturing. Like defeaturing here would mean that you can remove fillets, chamfers, or any splines or holes which are not of important consideration, which would not affect the results. Bolt holes, bolts, all those things which are not required. For example, in this case, let's say that if you are trying to do a modal analysis of this only the top part, then it means that what is your result, what is your key component. Let's say if you are trying to do the frequency test or modal analysis of this particular component, then you would not require these components which are small motors and all those things. You just try to eliminate those things and only look at the interest region. So that's how the model featuring works. So similar fashion in tower, we also eliminate bolt and bolt holes. I will go through those things in the next couple of slides. Then the case of adding a lumped mass, usually they do during the modal analysis or the Campbell plot frequency analysis, as it is said, we don't consider the whole assembly, only it is considered as a lumped mass to check how its effect is on the tower. Next thing is how the contact between the components is, and then the meshing of the body. Is it to be done on a solid meshing or is it to be done on a shell meshing? Then perform a modal analysis with lump mass and without lump mass, considering different kinds of material, and then validate your results. I'll walk through each of those cases. What are the design considerations? It This theory can be applied to any kind of design when you're trying to evaluate what is the natural frequency of a body, and then will it try to resonate when it is in actual operation. Be it any kind of machinery or be it any kind of assembly, you can do a simple frequency test which will try to determine the natural frequency of the body. So why the reason why we are keen with the natural frequency is that every component here has its own natural frequency. It doesn't mean that I have to test each and every component to do a model analysis and check okay whether it is trying to resonate with the structure or not. That's not the intention when the complete model is taken. So the intention in this case here is only to for the tower, but then when there are components are rotating, then the frequency test is again done. So that is again a different case altogether, how the frequency analysis is performed. As I mentioned, the each step-by-step process. This is how it would be looking like in a simple flowchart point of view. The basic relationship between the frequency and mass is that what you see on the top right hand corner is this the fundamental equation, and any natural frequency or the fundamental frequency is inversely proportional to mass, as well as, and it has a direct relationship with stiffness. So when we consider different designs, so as I said that we are doing a lot of iteration with the top mass. So the top mass will have change in the slight variations in the generator actual mass to what was initially estimated uh, based on the different designs of this main frame of the tower on top of on this nacelle. it will have different mass in the initial estimate, and the final mass could vary. But then the final mass which you try to do as a top mass, like let's say 27 ton, should not be in the final mass, say at 40 tons. So that's not an actual close estimate. So when you're trying to estimate something close to 27 tons, it should be in the range of like 1 to 2 tons can be omitted, or even at the max 3 tons can be omitted. So that is what the closest approximation or a top mass estimate should be. It shouldn't be like the case of you are estimating the mass at 50 ton, and in practice you are doing a 25 ton. So that's the reason lump mass plays a key role. And how does this affect the wave frequency? Yes, it does that. So this tabular column is have made it in such a simple fashion for all of you, that the parameter and what kind of activity is considered, whether it will affect it, and what is the actual example, how the parameter would affect. So going on the geometric structure, that's the complete actual model. So you would vary the thickness and the dimension, length, everything. So all of these consider again into adds up to mass of different values. So that when you all put together again is an inverse relation to frequency. So that again affects the model parameters or the fundamental frequency of the tower or any geometry of interest. Then the contact. What does contact here is means as each body makes, like let's say for example in this case that each shell is interacting with each other. So how do we consider in this case a contact definition? So if I put a frictional contact? What if I put a bonded contact? What if it is frictionless? So does those things affect my modal analysis as well as the frequencies? Yes, it does to a very large extent. Let's say that your contact plays a major role based on the material type as well as the force that passes through the tower. So that is how contact definition is. Like here in this case, it is between the welded sections to this welded section to this welded section, and also how this face of this flange is interacting to the face of this flange. So when we consider this as a tower as a whole geometry, each shell is also considered in the picture. We don't just design it as a cylinder case and then put it as a model. I have the closer and more realistic you try to put up the geometry, the better and finer the results will be. So that's how contact definition plays a major role. When we change the material, so as I said that different kinds of design for tower were there. So let's say there is concrete and the steel mixed. So you will define different kinds of material to these and different kinds of material to this, and then you can see how's the variation of the model analysis, because concrete has its own natural frequency and steel has its own natural frequency, and then blade is again a different material which is glass fiber, so epoxy glass fiber, then that has got its own natural frequency. So you are seeing here different kinds of frequencies from different components. So material plays a major role. Then finally is what kind of results are you trying to evaluate based on why turbine, for turbine design specifically, they especially the tower design, 1P, 2P, and 3P are the first important consideration. That's because your blade is trying to resonate with your natural frequency of the tower. They would make sure that 20% the resonant frequencies are away by 20% at least, or bare minimum 10%. So that in those regions, if you are trying to make sure that when your natural frequency is designed away by 10%, then you are making sure that you have added enough stiffness in your structure and it doesn't resonate in those operational modes. So let's little bit go to the actual model. So this model is the actual model that has been parameterized as well, as in the sense that if you are changing the lens tomorrow, you don't want to create everything from scratch. So each shell and each thickness is all parameterized. That can be parameterized in Ansys. What does parameterize means is here, like if you are changing the thickness, what is actually manufacturing standards, then you can put those thickness and put those actual lengths, and then you can do the complete model analysis rather than going and changing each time and recreating the whole thing. So this is how the faster way of the model development takes place. So defeaturing here would require you to remove all the chamfers between the welds and all those things, and door openings, bolt holes, which are all not necessary. So I can jump you straight to the actual Ansys environment. Um, the actual tower, how it would look like is what you see here is the shells. Each shell has been welded together and developed, and you can see here in the tree structure how the segment each for the segment 3 here refers to the top part where all the taper parts are considered having different frequencies. So each segment will have its frequency, but then we are all combining it together. There is, as I in the slide, I did mention about solid and shell meshing. So we will not. This whole part is an actual solid geometry. Uh, when you try to perform it full solid meshing, this would take heaps of time, probably more than 3 to 5 hours, or even a day, or at least 2 days in total. In case when you're trying to do a complete solid meshing, so it is not recommended that when you are considering geometry of such a height, which is about 70 meter in total and diameter is about 4 meter, it is not advisable to go for a solid machine. The reason why I can tell in the next couple of slides as we go through. So this is how an actual geometry feature would look like when you get it into Ansys environment. Now let me go through the furthest. So I've created it a simple snapshot. What I did was that I took a geometry model from AutoCAD Fusion and then imported it as a surface model. What is the reason that I did a surface model? I can explain using the slides. So before I go to those shell meshing features, I did mention about the contacts between the bodies, what would happen. So if you are considering only the solid bodies or even the shell bodies between each, and you have to, in real case scenarios, this is how the listing of contacts will be, like face to face, and then the bonded contact definition that has to be defined between each body. Usually, Ansys has an option of automatic detection between those bodies. Sometimes it would not properly be able to contact between those immediate surfaces. You have to make sure those surfaces are not interacting because they would consume additional analysis time. So as I mentioned that there are different kinds of contacts. So here in the picture on the right is what, as you see on the drop down, probably I can show you in a better format. In this case of surface model, you will not see those contacts. That's because the reason is that I have combined all the shells into one structure, so you will see only single contact. That's the reason what you're seeing here is a single contact. There are no additional contacts between the bodies here. Why did I do that? Is that because Ansys in student version doesn't allow more than certain, probably 50 bodies, or more than there is a weight and as well as nodes element wise constraint. So but then still I'm able to show you the results with limited restrictions in this. So let me walk you through the. Apart from that, what I want to also highlight you is that you can do also the modal analysis just by making sure that whenever there are multi-body assemblies and you don't know whether the contact between those bodies are properly established, you can just do it as a like a shake test. Like when you try to shake it, the bodies which shows almost zero or doesn't or shows completely flies away. In actual, when you do the practical case, you will come to know that the bodies which doesn't show proper results. It means that the contacts are not properly established or the load transfer is not properly taking place. This is another way of doing model analysis when there is large complex assemblies present in your assembly design body. So I tried to show you here directly how a solid meshing would result. So in this case, I tried to do a solid meshing on the bottom part only, and it came as the face meshing as a fail because face meshing was not properly suitable for a solid body component here. This one, the bottom is a diameter is about 4 meter diameter and thickness is about 20 mm. So you could see here that what happens is that the issues with the solid meshing is that one thing is that you have to make sure that the through thickness, like say here, the thickness is 20 mm, at least it should have two elements through the thickness, and it doesn't properly do solving if there is only one element to the thickness. As you see here in the flange, that there is only one solid meshing or solid element that is being put it across. So when I tried to do this, this is the total number of nodes and elements that it resulted when I meshed it. But then there is a limitation that beyond 2 lakh element or 2 lakh nodes, Ansys in academic environment, it won't be able to solve. So going to criteria, why do we need to do face meshing or using the mid-surface criteria? Is that what we try to do here is like make it as a surface model, and the surface model is done using a mid-surface extraction and then apply a face meshing. So in order to apply a face meshing, the criteria used is to make sure that the diameter to thickness ratio is less than 0.05. So here in this case is like my diameter is about 4 meters and the thickness is about 20 to 30 mm. So when you consider those ratios, you can apply face meshing on a body of such size. So let me directly show you how did I do this. If I directly just so when I import the body in this, it would ask me what would be the thickness. So since it is a surface, here the thickness as being considered it is only 10 mm. I've applied it as a uniform thickness, but in actual case, the thickness will be defined based on each shell. So you will be defining for each shell what is your thickness, and then you can parameterize using this the option here. That is how you have to do. But then this is a demo model case, and it won't be the same as what you would do in real case. So in real case, you will have all the shell surface bodies. For each shell surface body, you have to be defining what the actual thickness was considered for manufacturing purpose. So when we define as we get the body, it is all in one as a single body. There is no contacts, nothing. So that's the reason you don't see any additional contacts or nothing in place. This tower model doesn't have even the flanges in place. So here the condition is just a tower by its own natural frequency. So the coordinate system is the basic coordinate system. This is how it is also followed here. In this case, the global coordinate system, as we see here, is the z direction is in the direction of being tower height. So Going to the mesh. So how did I perform this mesh is, let's say I can probably remove this and tell you an option right from the beginning. Let's say this will how the default would look like when I try to put this. Let's say you have an option to do different kinds of methods, and we don't have mostly the methods is used for solid meshing. But then we have directly, since it is a surface model, we can use directly the face meshing model option here. So the moment it asks what to consider, so we put the surfaces in here. In this case, is two face because there is a problem with the geometry. But then in actual case, you will have shells for each surface. So you consider the whole geometry. I didn't put any enforcement of what would be the mesh size. You can define that as well by considering what could be my sizing. Let's say that without considering any sizing, we want to generate the mesh. You can see here, this is how the mesh would look like. But then when you try to put you can compare the results of these results and then see change the sizing, and then you can make a comparison. You will be able to distinguish if it is affecting the results or not. So let's go by the basic mesh method itself without having any sizing. Now, in order to put the boundary condition, what I did here was, as the tower in actual scenario with the foundation gets fixed up, in actual case, it will have a little bit of bending as well as rotational effects. But to this one is a fixed support, it means that it is constraining all the six directions of freedom. That is like there is no XYZ moments as well as displacements in all the six directions. That's what fixed support means. In this case, I have not considered any top mass. It is just like the tower on its own. We are having, and we try to find the natural frequency of the tower. So I use the option fixed support using an option insert, and you can find various boundary conditions that can be applied. So in this case, the next option you can also try is having a simply supported, in the sense that it could have some constraint, or you can use particular displacement effects as well, like in which directions you want to constrain the motion of the body. So based on that, these boundary conditions are formed. So here, when we try to solve this, it would list up basically without these deformations as by default. Let me delete this and show you how this comes up. When you actually see the results, it doesn't show you any of these. Go back. So what you see here is, as it has solved immediately, and it has listed out basically the modes, the first six modes. Why it is listing only the six modes? You can get beyond that. Let's say if I don't want more than those modes, then you can change it to, let's say, 10 modes or 15 modes. But then what does this mean is that, like, let's say that you know a particular mode shape or a mode frequency of interest, then you can increase those mode numbers and then try to see what's your expected frequencies. So in this case, let's say I put up a 15 modes in this, then it would try to list me all the modes in that, saying that these are the 15 modes. But then that's not my important criteria as far as the tower is concerned. My first criteria is only the fundamental frequency, the 2P and the 3P. Why is the reason is because of the blades is having three-bladed structure, so to 3P is important. You can also see the 6P as well if it is a six-bladed one. So that's how the number of modes is taken into picture. So let me try to put how the graphical part looks like for each of these. I select the whole of those and try to create the mode shapes. Then it would result me here, ask me to solve again. I evaluate the same results. Now you can see is that um, trying to put up the graph for this. Mhm. Modal. Okay. Okay. What I wanted to show you was that how the actual animation takes place. I'm not able to find where to make the case. Okay. Yeah. Okay. Mm. So what you see here in this case is the at the first natural frequency it is completely undeformed. When you try to go into a true scale, that's the same. When you try to zoom in, this would be the case. Like what it tries to tell is that what's the maximum deformation at the top, which is at zero point 0.2 mm. That's very nominal, and this does happen in actual case as well. When the natural frequencies are there, you would see different kinds of modes. So in this case, that it has been oscillating in this way and the other way. Let's go to the third one. I'm trying to figure out the play animation for this. Amos, do you recollect where do you play the graph for this? Yeah, I've got this here. So this is how the animation effect would look like. Let's say this we have a more time delay and see that in a slow fashion. So in the first mode, this is how it will be oscillating in the natural frequency of 0.8 hertz. So when we change that to a second mode, how it will look like is in a different fashion. And in third mode, you can see it will be in a different, what it is meaning here as per the pictures here is like it is trying to make a sinusoidal effect. That's how the actual effect would be. In practical, yeah, in field, yes, you will come across all these modes, and they are all realistic in nature. So let me go through, walk you through the other part. Like what I've done in this demo is that I have considered the same structure surface model, and I have added a point mass. So in order to, if you have to add a point mass, all you need to do is using this option at the top and insert and do a point mass, insert this. It would ask you what's my coordinate system where this remote mass has to be. and then you can define, as we said, that the turbine is sitting at a height of 74, 73, 72 meters. So the center of the nacelle is somewhere 1 meter or 1.5 meters above that. So that's how you define this location. And we estimated that the tower top was about 27 tons. So I additionally put 30 tons. And to check, you can also parameterize this when the mass keeps changing, or the whole mass of the tower is also changing. As in this case, I also consider the feature of having a flange at the bottom so that I properly fix the surface. And the definition of the whole structure is structural steel, which is the basic default option that comes in the Ansys engineering material. Now, in this, you could see that there are two kinds of contacts. So one is the contact between this surface and the surface on this. So here you would be able to see that definition. That the contact of the target body to the shell surface. Now, is that correct or is it incorrect is what you have to define. Like if this body's surface is touching close to that, then it will try and detect that this is the actual surface, contact surface. And the next surface is this top surface trying to touch the edge of the shell. Now, going to again meshing, I did show in my first case, the mesh is has got elements at 512 and 504, because there are two couple of components are not there. But then when you try to have additional body, let's say in this case that I did mesh, and when you try to zoom in the flange, you could see here I tried to force this particular flange at the bottom, solid mesh, which looks like all cubes fixed to each other. So I enforced the body sizing on it, having a 30 through the thickness of this 60 Sorry, this is about 80 thickness solid flange. So how did I do this option? You have an option to insert and see the method, where you can see and select what kind of geometry you want. You can select it, and then you can use these options. How do you want to enforce the element type? Then in that, again, with the method, you can insert the sizing, and then define, okay, this is my geometry of interest, and apply. By default, it has its own sizing. I would suggest that you have to iterate at least 2 elements or 3 elements through the thickness of the body of interest. So here I enforced 30 size at least, and then it was able to quickly mesh the body. So let me delete and show you how this gets done and clear the data. So as this particular body is completely shell, just the surface, just like a paper, we do a face meshing for that. So now I generate the mesh for this complete structure. So now you can see here the difference in elements and nodes compared to the body which didn't have previously the flange. Next in the step is, let's see, we try to solve the case. We don't have to put any additional force or anything. We just insert the constraint and add the constraint at the bottom of this flange. We haven't actually considered in actual case foundation is also plays a major role. So how foundation is also part of the simulation is that they would consider a big cubical box twice the size of this bottom flange, and then they would put a cubical stiffness to that foundation that's equal to the soil stiffness, and then they would do a coupled modal analysis and then check how the frequencies of the tower structure is. So that's another case. In this case, we are only restricting the demo to only having a lumped mass on the top and having a flange at the bottom and having a single material. We are not changing the material to any other materials. We can also do a study by just splitting it in three different parts, and do two steel and one concrete. So we can check the results, how it varies. I will be sharing those results to Amos, and he will be able to share it with you. So in this case, let's solve what happens when you add in 30-ton mass on the top. As you see here in the process, it's preparing the complete mathematical model. What it would do at the background is prepare the element matrices and try to solve at each in those locations what is its complete frequency of those locations are, how the variations are throughout the length of the body, and then the deformation as a format of result. Now in this case, let's try to solve. So here you could see that by default it has generated 6 modes. Let's see how it looks like in the you see here that the first two modes and the rest of the modes are not everything is showing 000. It means that there is definitely what it has done is not properly solved the model, and when you try to get the mode shape results, you won't be finding the same thing as what you have done in the first boundary condition. So as I said that the transfer of forces or the transfer of the top mass to this structure didn't properly apply. That's why you are seeing this incorrect result. So in order to evaluate where is the fault, you have to go back again and see how the mass interaction or the contact interaction between the bodies are. Probably I'm trying to show you a direct live demo and seeing the results where to diagnose the problem. Let me suppress this and this particular contact because it has no relevancy. Additional surface which is not required. We have top mass and it is linked. What it does is it will interact, it will ask you to how this top mass is going to interact with this body. So I've defined here that it will interact instead of flange just on the edges. Sometimes this can also lead to incorrect results. Let me again solve and see how the problem comes, how it solves. Are there any questions that you would like to ask? So again, the results are coming as 000. It means that that's not the correct way of analysis. So we'll go back to this first boundary condition. What we did here, we did see that, okay, it was a simple case of fixing the boundary and no top mass applied, but then it was able to give us the results. These are the actual results. Now, if you try to see what's the frequency of this or the rotation RPM, so let's say here in this case, the first fundamental frequency is 0.823 hertz. So you multiply that by 60 and see this RPM is 49 RPM. Let's say if there is a tower that if there is a turbine that has been designed where we are seeing 49 RPM close to that, then we would try and see that we are improving the tower's thickness or stiffness of the whole structure and keep it away from this RPM, or make sure the other option is to see that, okay, if this RPM cannot be avoided, then you have only the control systems as your major function to uh, increase or decrease the RPM whenever it is coming close to the natural frequency of the tower. So coming back to the slides, so I'm not show you what is the reason why it is not able to solve, but then that is another case to again to show you how exactly things can go wrong if you are not trying to know what the end results are. So that particular boundary condition 2 is incorrect. So we can do again an iteration of that and redefine probably a flange on the top and see how the interaction of the bodies are and what's wrong with the geometry and diagnose the results and check how the frequencies should be. So coming back to the demo, so in this case, we just did this, as I said, in the having a point mass at the top. That's action is also done in realistic case. And then we also do another iteration of different materials and then check again the frequencies, how they are based on the turbine design. And then you can do this. I'm happy to share a model and the size of this geometry, and you can explore on your own what are the results, and you can come back to me over email or a communication mode to discuss results, what is your finding and what are your thoughts, then and see how you play on your own with the demo version. I probably we are before time to wind up the demo, and if you have any questions here that to ask. As far as the demo is concerned, with the modal analysis, it is pretty short in terms of the analysis is done. The only thing is that the variations, what we see is based on the thickness, because here we are not talking about how when you vary the different, because when you do in actual practice, you will be doing mid-surface extraction of all these surfaces, then applying the thickness, then meshing of all these components, then applying a single type of material, then a combination of material. That's how the actual case would be. The demo will take beyond this time. But then I was trying to show you a simple structure where I created it as a cylinder and a taper model combined in one shot rather than having so many shell elements. Yeah.
Yes, Mr. David. I'm Mr. Khan from Oman, Maritime College, Oman. So, yes, please forward our wishes and appreciation to this man. Really, he did very perfect presentation with good calculation and deep analysis of all his presentation. So, definitely, it was a 2 hour session, but behind this 2 hours, about maybe 2, 3, 4 weeks are involved for this hard working. So, I really appreciate his effort. So, congratulations. It was excellent presentation.
Thanks for the feedback. Yes, what I try to show you is only a short film, but then it
Hmm.
definitely takes a long time for us to,
True.
because I'm fortunate that I had the knowledge of the dimensions and everything, and some materials which were I was able to recreate so that I could show in actual what's the actual practice. Um, Again, thanks for this.
Good job. Good job. Thank you.
Any questions that any questions that you can think, even if it is a stupid question, you can ask. Nothing wrong. But then everything is in terms of when you try to design and do engineering, all parts has to be considered. What you would have observed in this demo is that the internal assemblies are all not considered within the turbine tower, so that's all omitted. So that is also part of the defeaturing. Some of the concepts even, I may have omitted. You can feel free to ask or reach out over email or LinkedIn, and I can share more thoughts on that. Yeah, some mic issue. Mhm. No problem. I think we've got a communication issue.